Studies at Lambda Laboratory currently cover low-density experiments of magnetized non-thermal plasma, MHD accelerators with various shapes, ionizers, streamer guidance, and plasma wall confinement system. The activity of the French Lambda Laboratory, created in 2007, as a continuation of a long story, whose starting point lies at the end of the 60s. In the Institute of Fluid Mechanics of Marseille, a small team of researchers worked on MHD power plant. This one converted the energy of a shock-driven hot gas flow into electricity. Due to its high electrical conductivity, 3000 sieverts per meter, and high velocity, the interaction parameter was so large that the experiment produced a front shock wave in a constant cross-section MHD channel. Then an idea arose: if it is possible to produce a shock wave without any material obstacle, would it be possible to prevent the birth of shock waves around an object cruising in a gas at supersonic velocity? On this picture, you can see the shock-driven wind tunnel installed in the Institute of Mécanique des Fluides of Marseille in the middle of the 60s. Here you have the combustion chamber filled by hydrogen and oxygen plus helium. Next you see the tube, the gun, 6 meters long, constant cross-section, 5 centimeters per 5 centimeters. It was filled by low-pressure argon. When the combustion was ended, it opened a metallic diaphragm that you can see on the left, and the shock wave was running along the tube, breaking a mylar diaphragm at the end. Here you see the MHD converter with its 2 coils. The length of the converter was quite short, only 10 centimeters long. The arrow shows the 2 coils giving a 2 Tesla magnetic field given by the discharge of condensators, and the intensity was switched by ignitron connecting the 54,000 amperes current. On this slide you see the schema of the shock-driven wind tunnel. The test duration was 100 microseconds. Again, on left, the combustion chamber, the metallic diaphragm, a trigger, the constant cross-section tube, 6 meters long, filled by low-pressure argon, the mylar diaphragm, and the vacuum tank. The pump, argon bottle, manometer, pump, condensator bank, ignitor, 2 Tesla B-field coil, and the Faraday MHD converter. We achieved 2 kinds of experiments. In one, we produced energy from the kinetic energy of the gas, and in the second one, acceleration was achieved injecting energy from a secondary condensator bank that you can see on the slide. Well, here you have the parameter of the argon flow. The gas temperature was 10,000 degrees Kelvin. The velocity was 2,750 meters per second. And the pressure of the case was 1 bar. On this slide you see the hot fast argon, compressed argon, quite short, only 20 centimeters long. And here we build a Faraday converter. The Faraday converter is made of two components. The channel, you can see the two coils, and you had segmented electrode converter. Here the electrode pairs are connected to loads, and here the electrodes are in place. Below you can see the induced electric field V cross B. This electric field produces electric current J being the current density per square meter, and this current density creates a volume force G cross B that slows down the fluid. And in this middle of 60s, there were a lot of power plants over the world, but the low electrical conductivity of these big devices was too small to extract a lot of enthalpy from the fluid and to slow down the gas really. So it can be expressed with the value of the interaction parameter. In the other installation, the interaction parameter were low, and in-house it was high because we had a very high electrical conductivity due to the high temperature of argon. Well, here you have the classical pattern of the Mach lines. Mach lines which are real when the flow is in supersonic condition. And from left to right you see how these Mach lines change with as fast as the faster the velocity, the smaller is the Mach angle alpha. Well, all these things are well known. Well, when we work with the MHD Faraday converter as a generator of electricity, the fluid is slowed down, the power is extracted, and the Mach lines are straightened up. Well, we operate the converter as an accelerator. We inject power using our condensator bank. The fluid is accelerated and the Mach lines are bent. Now, if we go back to the generator, if the interaction parameter is high enough, the change in the Mach line will be so strong that a shock wave occurs. And the birth of a shock wave is caused by the accumulation of the Mach lines. And we were surprised in our experiments to see a plane shock wave installed at the inlet of the generator due to this very, very strong interaction parameter. Well, this shock wave was evidenced by interferometric imaging in 1965 at the Institute of Mécanique des Fluides of Marseille, which no longer exists now. Let's point an important feature of such experiment. Lorentz forces are very efficient to act on a fluid. GB are volume forces, and these volume forces can be very high. Take for an example 1 ampere per square centimeter and a B field of 1 Tesla. Look at the force. It corresponds to 1 ton per cubic meter. Well, acting on air in normal condition, it provides an acceleration of 1000 g. So we open on a different fluid mechanic in which the pressure and the velocity and the pattern of the fluid is completely controlled by the Lorentz forces. And the inertial forces could be neglected. Well, many years later, we tried to restart this research and to see if shockwave could be cancelled. But we had no shock-driven wind tunnel available, so we shifted to hydraulic simulation. Hydraulic simulation are very good simulation for shockwave. When I was a student, computers did not exist, and we used this hydraulic simulator to understand the behavior of shockwaves. When you have a free surface fluid, if you move the bulb of line, you make circular waves, and the circular waves expand at a velocity which is the equivalent of the sound velocity. Well, now if you move the source of the oscillation, if you move the bulb at a velocity slower than the velocity of the circular waves, nothing happens. But on the right, if you move the bulb at a velocity higher than the velocity of the surface wave, then you produce waves which are the equivalent to the Mach line of the supersonic flows. Here I point the analogy between on the right the flat shock waves installed around a flat wing moving at supersonic velocity. In A you have front wave, in B bottom wave, and on the left the wave around the hull of a ship are similar to the front and bottom shock waves, which form around a flat wing cruising in air at supersonic velocity. So the question is, can we cancel or prevent the shock wave around a body immersed in a supersonic gas flow by suitable action of a G-Bay field? So if we move this problem in hydraulic velocity, we will consider a device with a free surface flow, that you can see at the top. The liquid is water plus acid to get enough electrical conductivity, and we used MHD cylindrical accelerator. Well, the principle of the cylindrical accelerator can be seen on the feature below. The cylinder is just a solid magnet with 2 electrodes, and these electrodes produce a discharge in water, and this current density combined with the magnetic field produce Lorentz force that tends to accelerate the fluid. But as you can see on the figure on the right and below, in the vicinity of the electrodes the fluid is accelerated, but in the front part left you see it slowed down, so it gives continuous and soft slowing down of the fluid. Well, this picture shows this cylinder MHD accelerator working and how it sucks the water on left. The picture is not so good, but you can see that the turbulent wake is cancelled completely. So the central question was, is it possible to move a body in a gas at supersonic velocity without noise? The noise has 2 causes. One is shock waves, but the second one is a turbulent wake. And if we cancel the turbulent wake, we cancel this source of noise. Well, here we return to this cylinder object placed in a free surface fluid flow and at a velocity higher than the velocity of the surface waves. On the top, what happens when no Lorentz force are applied? You have strong waves, front wave and bottom wave, and a turbulent wave. And below you have profile. You can see in black the electrodes, and I have represented the level of the water. Well, if we want to act efficiently on this flow, we have to achieve interaction parameter that would be large enough. This is the expression of the interaction parameter. If we use 8 centimeter per second flow, the computation gives that we need a 2 Tesla field. We cannot play with the value of the current density because of electrolysis. Electrolysis will completely destroy the experiment. In 1976, we achieved the cancellation of the front wave by Lorentz forces. As you can see on this picture, below the large value of the interaction parameter, left the force field, and right the results. Of course, we didn't cancel the bottom wave, but the front wave was completely cancelled. And as you can see on the figure on the right and below, the level of the water was depressed. If we think about an analogy with gas, it means that if you act on the fluid with Lorentz forces strong enough, not only you cancel the shock wave, but you can create a depression in front of the machine. Well, this was presented 6 years later by Jean-Pierre PETIT in the International MHD meeting of Moscow in 1983, and this trip was totally paid by Jean-Pierre PETIT. Well, you will not be surprised that this kind of research were not accepted with enthusiasm by the scientific community because of soft connection with undesired phenomena. Well, here you have on the left and the top the characteristic lines around the flag wing as you can compute them with a computer. This is classical, and where this line accumulate, there are the birthplace of shock waves. So if we want to prevent a shock wave formation, we have to maintain the parallelism of the characteristic lines, of the Mach lines, and this can be done with 3 pairs of electrodes, because as you can see, we have to accelerate the fluid at the leading edge, but we have to slow down the fluid in the middle of the profile and then accelerate again. So the schema of the forces is given on the left and right, as you can see. Well, if you think about hydraulic analogy, the pressure is equivalent to the level of the water. And if you want to prevent the birth of waves, you have to keep the water flat. That's very simple. So a basic idea arose. The gas fluid mechanics could be split into 3 domains. Supersonic flow with a subsonic flow without shock wave. Supersonic flows with shock waves. And then a third one, supersonic flow MHD controlled without shock waves and without turbulence. In the mid of the 80s, we tried to set up a research program towards shockwave cancellation by Lorentz force field. The idea was to find an old shock-driven wind tunnel and to operate into a hot supersonic argon with high electrical conductivity and sufficient interaction parameter value. We found the shock-driven wind tunnel in Caen, France. We found high-capacity condensators, ignitron, everything. A student, Bertrand Lebrun, achieved a PhD thesis computing all the required parameters to run the experiment. Well, this is a quite original way how Lebrun did this calculation, for in those times the computers were very slow. I think about a normal computer. We used Macintosh units with 2 megahertz clock and 500K for central memory, so it was absolutely impossible to run today's simulation with such machine. So Lebrun used 6 machines, and we were one of the first to operate a multiprocessor technique, because we had 6 multiprocessor technique, but the connection was obtained with a motorcycle that you can see there. Well, this is a result of this 2D computation, and now you can do that very easily with modern computers, even with one microprocessor, because they are so much faster. And here you can see how Lebrun obtained a different pattern from Mach lines, which tended to think that shockwave could be cancelled. This was presented in 2 MHD meetings, Tsukuba in Japan, 1987, and Beijing, 1988. And it was published in peer-reviewed journal. Well, of course, we had no money to go to Tsukuba and to China, so the paper were just included in proceeding. In the peer-reviewed journal, it was easier. This new technique suggested that supersonic and even hypersonic flight in dense air could be possible without any noise. Well, due to evident connection with UFO case, the French official, scared, preferred to give up. Funding was refused. The scholarship of Lebrun, extended over 2 years, was used up. After the publication of papers in top-level peer-reviewed journal and acceptation of communication by international meeting boards, to which we could not attend due to complete lack of money, Lebrun abandoned research, created a company devoted to combustion simulation in motors. I went back to pure theoretical research, kinetic theory of two-temperature plasma, astrophysics, mathematical physics, cosmology. Except my salary in the French CNRS, I was deprived of any funding during 25 years until retirement. Everything was gone with the wind. Everything was gone with the wind. Anyway, the French CNES, Centre National d'Études Spatiales, a national center, French national center devoted to spatial studies, had created a service called the GEPAN. GEPAN was a groupe d'études des phénomènes aériens non identifiés. It was a group devoted to the study of UFOs. It was created in 1977, and they tried to run some experiments by their own in a military laboratory located in Toulouse, France. Here you have 2 pictures of this installation. It's a subsonic wind tunnel on the left. On the right you can see in 4 the cross section of the tunnel, and they put the cylinder accelerator in this channel and tried to see if it was possible to cancel the turbulent wake. It was an idea that I suggested in a letter in how to evidence the reduction of the turbulent wake in the air. Just put a microphone on the wall, and if the level of the noise was reduced and even suppressed, it would mean that this turbulence would be reduced or cancelled. On the right, you see the two big coils producing, I think, a 4,000 Gauss field. And it was necessary to create the ionization in the channel. In my letter, I suggested to use 2750 megahertz source for ionization creation, which is a standard. So they built 2 megawatt source and tried to ionize the gas. The way they did is shown on the left down. You can see the microwave wide, the window made of Teflon, but they ignored that. Everybody knows that if the air is ionized, the electromagnetic waves cannot cross it. That's why you cannot communicate with an astronaut when he's doing his re-entry process in the atmosphere. So they had ionized layer and nothing else. And the ionization could not be installed around the cylinder. So they gave up, and unfortunately were not asked to participate, because if I had been asked to participate, I would have given the solution immediately. The solution was to inject the microwave by the model as shown on this slide, and then inside the cylinder you put some material that scatters the waves all around, and then the ionization is installed very close to the model, exactly in the place you would like to see this ionization to be installed. Well, in those mid-80 years, it was the end of the French MHD. 20 years later, three guys, Jean-Christophe Doré, Mathieu Adair, Xavier Lafont, asked me to run MHD experiments. I was retired, but I accepted. Jean-Christophe Doré offered 15 square meters home garage facility, so we have a place to install some experiments. And well, we needed money, so we tried to get some, and I wrote a book, and we printed the book, and Doré, Adair and Lafont sold the book, and it brought 50,000 euros. So we had money to install experiment. In addition, we had the help of two engineers, Jacques Le Galland and Jacques Jean. They were retired, but they offered to help us without being paid. So we had a good research team. We had money and a very, very small place. Well, you can see the results on this page. Here I mentioned the first paper of 1983 in Moscow. I mentioned the PhD thesis of Lebrun, some publication in peer-reviewed journals. So this is a proof of what I said before. And then we had the first meeting in Lithuania, in Vilnius, for MHD, that was presented in 2008 and then published in peer-reviewed journal Acta Physica Polonica. We had another paper presented in Germany, in Bremer, a meeting devoted to hypersonic processes, and then another one in the International MHD meeting of Jeju in 2010 in Korea. I will insist about this word because we have pictures that are quite impressive. Well, we operated a wall confinement technique by magnetic gradient inversion. It was presented by me and Jean-Christophe Doré. Jean-Christophe Doré built an apparatus with a transparent glass chambers. Experiment in low-pressure gas makes possible to get high Hall parameter with simple solid magnets and glow discharges with moderate voltage. It's also reproduced somewhat in high altitude for hypersonic flight problems. The electrical conductivity becomes the following matrix, where beta is a Hall parameter. Here you have this matrix. In black, the scalar conductivity, in red, the electrical conductivity. When, the Hall parameter is low, the conductivity is close to the scalar conductivity. But at the opposite, when we are in high Hall parameter regime, then the conductivity is matrix, but as you can see, its four components are very reduced. The parallel components is reduced by the square of the Hall parameter, and the transverse component by the inverse of the Hall parameter. So you have a tool to create a non-homogeneous electrical conductivity design. So here this is the plant built by Doré. Here you can see a cylinder, large size, in which we can create with a pump. This is a vacuum bell. This is a pump. And here's a small model, 6 or 7 centimeters large. And here's the electrical supply. Well, as we use high voltage, it is not convenient to move the things with the hand, so Doré installed an electric actuator in order to move the magnet represented in red. Well, this is another view of the installation with the actuator, the confident magnet, the disc-shaped model, below you see the pump, the electric device. Next slide, an axisymmetric model of a MHD disc-shaped aerodyne put on a cylindrical solid magnet. We use solid magnet because if we would like to produce a field with a coil, the intensity would be too large, so it was easier to do that. On the top of the model you have a belt of segmented electrode, and in red you see the line for magnetic field. You see that this line expands. So if we want to make the current flow from A to B, the magnetic pressure will tend to push the discharge away, and that's exactly that you can see on this picture, because here you have the electrodes, segmented electrode in B at the top, and a continuous electrode in A. And here you can see the characteristic pattern of the discharge. So we wanted to keep this discharge close to the wall. So the idea was to modify the geometry. Here this is more precise. You can see the glow discharge, the segmented electrodes, and the magnet. In an MHD aerodyne, the magnetic field would be created by a coil, not by a solid magnet. In the precedent images, this B field would be created by an equatorial one. In order to keep the discharge close to the wall, we had a second coil with opposite electric current. This modifies the magnetic geometry so that the magnetic field is maximum at some distance from the wall. Then the magnetic pressure will press the discharge close to the wall. In other terms, back to the matrix form of the electrical conductivity, the discharge will follow the minimum resistance path. This second coil effect is simulated by a second solid coil with opposite polarity. Here you can see the intensity of magnetic field. The strongest is given by the color yellow, and here in white we have represented what behaves like a magnetic barrier. So this is the expected magnetic wall confinement expect. Here you have computed the value of the magnetic field and the value of the magnetic pressure. Left you have the value of the magnetic field. As you can see, it's maximum in B, and it's correspond to this part of design. And here is the value of the magnetic pressure. Here, when the confinement magnet comes down, the discharge is progressively pulled to the wall. Here we have represented the two magnets. Up the top magnet descent starts the confining process. Now the glow discharge is fully confined to the wall. And here we have represented the position of the magnets. Of course, in a real MHD aerodyne, this magnet will be replaced by coils. This is another view where you see the actuators, the confinement magnet, the segmented electrodes. MHD aerodyne combine various techniques. Among those that create a discharge with electrodes, you can mention spheroidal aerodyne. The principle of the spheroidal aerodyne is very simple. It's close to the cylindrical aerodyne. I just show how it could be featured with a model. Here you have a rotating magnet and metallic brush that feed cyclically the pairs of electrodes. We would expect that to get this, but unfortunately Doré's garage is too small to install both plasma experiment and hydraulics. And Mrs. Doré firmly refused to host a fluid mechanics laboratory in her kitchen. A spheroidal aerodyne model from plasma aeronautic can be built as the following. You need 3 coils with 120 degrees dephased currents in order to produce a rotating magnetic dipole coupled with synchronized pairs of diametrically opposed electrodes. Well, in the future we will achieve this experiment for low pressure gas and not for hydraulic because of the attitude of Mrs. Doré. Well, the wall converter was invented in 1958 by Mr. Way, and we rediscovered it during the 70s. This MHD configuration makes possible to get the electrodes as close as we want each other. On the other hand, it confines the interaction in the boundary layer. It is used in hypersonic craft cruising at a high altitude over 30 kilometers, where the low pressures give a good electrical conductivity. This explains the myth of Aurora, and the Russians had a similar project called Ajax. At very high altitude, a flying machine must cruise at hypersonic velocity, so they use MHD control inlet that makes possible to slow down the air with moderate heating using what is called now MHD bypass, so that ramjets can be used. Then the problem of the source of an NJ is solved. But this kind of machine are uniquely designed for military purpose, so that the laboratory is not interested in. Let's go back to the disc-shaped aerodyne. The concept of MHD disc-shaped aerodyne was introduced by Jean-Pierre PETIT in 1975-1976 in two publications issued in the French Compte Rendu de l'Académie des Sciences de Paris. The first system is based on a set of spiral current streamers due to strong oil. Here you have the disc-shaped aerodyne Formula 1 and its spiral streamers and system of quasi-radial forces at the top and at the bottom. If the magnetic field is created by a single equatorial coil, the glow discharge is pushed away. This confinement, as you saw, was solved. This is a paper presented in Korea. Jean-Christophe Doré is currently solving the problem of the stability of the current spiral pattern. Looking at such strange shape, one can be puzzled by the apparent anti-aerodynamic profile with sharp edges. Keep in mind that Lorentz force runs the flow and overcomes completely the inertial force in the case. The second family of models is based on the induction effect. If we produce an alternative dipolar axisymmetric magnetic field by equatorial coil, this field combined with induced current will produce radial Lorentz GB forces that will be alternatively centrifugal and centripetal. If we combine this with a synchronized control of the electrical conductivity nearby the wall, we can create a lift. Here you have this synchronization of the B field and ionization. It depends on the phase, on the two features. It corresponds to the use of centrifugal forces at the top and centripetal forces at the bottom. Of course, we have to use 3 synchronized coils to have wall confinement. This is the shape of the machine with the three coil. At the top there are features, and to get wall confinement the current must be synchronized but with opposite direction. This gives this magnetic pattern, and here in red we have features the confinement region where the plasma is kept. And of course, if we can modulate the ionization when we create the ionization at the bottom, on this slide in pink we have features the ionized gas, ionized air, so that if it corresponds to the step where the forces are centripetal, and in the other we have centrifugal forces. This last picture shows some attempt to modulate the ionization by hyperfrequency, but the shape of the disc-shaped machine produces immediately hyperfrequency electric arcs. This is beautiful, but this is not what we need. Another solution, a better solution that we intend to use consists to create this ionization by microwaves. So on the feature on the top and right you have 2 cylinders that are waveguides, coaxial waveguides, with alternative injection of microwaves. And this picture at bottom explain how it works. Left, the central waveguide create ionization at the top of the model, and on the right, at the periphery, the waveguide create ionization at the bottom. So we could expect to have synchronized ionization and lift. Here I have presented mini-wave discharges in order to control the wall ionization. And this is first experiment done in the Lambda laboratory in 2011 by Jean-Christophe Doré with some hundreds of ionizers. This is not completely homogeneous, but you can see side view that we have quite good ionization at the wall. The disc-shaped aerodyne with current streamers function in 2 temperature plasma with high Hall parameter, immediately greater than critical value. Well, we will have to face the Velikov instability problem. In the paper presented in Vilnius in 2008, we gave the computation of the parameter of the Velikov instability that are not so much known now. Here you have the critical value of the old parameter linked to the 2 expressions there corresponding to the value of the ionization. And here you have the growth rate of the instability. This growth rate is positive if the value of the old parameter is greater than the critical value. So these are the results published in Vilnius and also some years earlier. The Velikov instability is a plasma turbulence whose rise time is comparable to the ionization time and strongly enhanced by its nonlinear nature. It destroys completely the desired spiral pattern of the discharge. Here we manage, Jean-Christophe Doré built a low-pressure annuli chamber with a cathode and a glass which makes possible to take picture from the top. And here you can see the Velikov instability gives this kind of striation which is opposite to the passage of the electric current. And here the curves that correspond to the formula given earlier. Here you have the value of the critical value of the old parameters, which decrease and then is kept close to 2. This corresponds to the Coulomb-dominated plasma when the electron-ions collisions dominate. And when the current density is increased, the electron temperature is increased too, the ionization is increased, the numbers of ions too, so that the collision frequency rises, and subsequently the old parameter falls, so that the conductivity becomes better. All this is combined and provides stable condition. We expected that. The local value of electrical conductivity corresponds to the following matrix. Left you have the electrical conductivity and black the scalar conductivity. If we manage lanes in the chamber where the B field is weaker, the local value of the old parameter effect will rise the conductivity so that the discharge will follow such lane, rise the electron temperature, rise the ionization and Coulomb collision frequency. The small magnets with opposite polarity with respect to the general B field, perpendicular to the plane of the figure, weakens its local value. And it works, as you can see. You can see the lane with weakened local value of the magnetic field, and you don't see anymore inhomogeneity. A full spiral pattern can be installed through fast sequential feeding of electrodes in order to prevent streamers interaction. The period of the sequence must be small with respect to the transit time of the air around the aerodyne. Back you have the spiral streamers and the expected flow. I have given a general view of our research. You see what we are searching for. We'd like to check if turbulence and shock waves can be cancelled around disc-shaped machines. We have a certain step to cross. We have done some. We have kept the discharge close to the wall. We have mastered the Velikov instability. Now we have to control the spiral pattern of the flux. We have to master the modulated ionization in order to operate the induction aerodyne. Then we will evidence the flow with a border and evidence of the velocity field. And at the end, I don't know when, try the final experiments. Thanks.